So I will be talking about a two-dimensional interface growth model. You have already seen very briefly the simulation of the model in one of Vadim's slides at the end, I think. And all right, so it will be, so you have an interface, it's a 2D interface. It will grow with time, well, according to some stochastic rules. Of course, it will be an irreversible process because it's, okay, we have a drift. And well, there are, not just for this model, but for this kind of, in this kind of framework, there are a set of very natural questions to ask. First one is about invariant states. Of course, since the interface is growing, only the gradients may have an invariant measure, not the interface itself. Then one can ask about, maybe I start from this invariant measure and I ask about height fluctuations and correlations between them at different space-time points. Another interesting question is about hydrodynamic limit. I start from a profile that approximates some smooth height function. I let time run. I scale space and time. It will be a hyperbolic rescaling, and I want to see whether I have a law of large numbers for the interface shape. And then in general, such law of large numbers are described by PDE, which of first order, which will develop shocks, then what happens then, and so on. So the goal will be to present one model. Actually, at the end, there will be an extension which are related to lozenge tilings, and where these questions can be answered quite in detail. All right. So, well, okay, this slide is no news for anyone, but just to set the stage, in 1D, in one dimension, the most natural growth process one can imagine is a simple exclusion. So you have a path which is just a zigzag, like that, and then you have, okay, I even have a pointer. So updates will consist in minima flipping to maxima or the other way around. And according to whether you do this with equal rates or different rates, you will have the symmetric or asymmetric simple exclusion. Okay, so it's like in terms of interface, it's like you are deposing, adding squares or evaporating squares with two different or equal rates. Okay, so I hope everyone has seen these kind of things before. Let me just recall something which is very well known, is that if you do the usual interface to particle mapping, that is, you draw a particle whenever the gradient of the interface is positive and no particle when it's negative, then the dynamics just corresponds to particle jumping right or left by 1, satisfying the exclusion rule. So this particle, for instance, cannot jump left, corresponding to the fact that here there is no maximum in this portion, nor minimum. And that the jump to the right and left will be P and Q, okay, either of them, depends on the conventions. Okay, so and then, okay, this is a usual mapping. And then what is very well known is that irrespective of whether you have P equal Q or not, if you start from a Bernoulli initial measure with some parameter rho, this will always be stationary in time. It may be reversible or not. That depends on P being equal to Q or not, but it's always stationary. In one, okay, for P different from Q, of course, you will see a flux of particles. But if you just look at fixed times, you always see Bernoulli. Right. So what we would like to do is to look at the similar model in higher dimension. And the natural way to go to higher dimension, well, higher will mean 2, is not to look at simple exclusion in 2 dimensions, because then if you look at particles on Z2 moving by simple exclusion, you cannot see them as a gradient of some height function. So in 1 dimension, you can always do that, in 2 dimensions not. So, but the right way to generalize this picture, so as I said, is not to go to 2-dimensional simple exclusion, but to look at rather the two-dimensional analog of the zigzag path, which are the pictures that already appear in very similar form, apart from the colors in Vadim's talk. So instead of having a zigzag path, you have a stepped or discrete interface. It's a two-dimensional interface in 3D. When you project it on the screen, it looks like a lozenge tiling. And it has if you take sections of this interface, sections parallel to the three orthogonal planes, you see just zigzag paths. Okay, so if you want, when you look at the height of these columns in the, let's say this is the x direction, or in the y direction, these are decreasing. Every section looks like a simple random walk path, but then you have this more complex picture. All right, so this will be the type of interfaces that we're looking at. So you can either see the model as a dynamics on lozenge tilings or a dynamic on these interfaces, as you like. All right, so the analog, the most direct analog of the simple exclusion in this context would be just, remember in simple exclusion I was just adding or removing squares with rates p and q. So I could do the same with cubes. Okay, so first of all, let's remark something which is very well known, is that if you look at a horizontal line, a vertical line here, along this line you will meet a certain number of lozenges, or horizontal lozenges, which are drawn in yellow. And if you look at the locations of all these yellow lozenges, they are interlaced in the sense that if you look at two neighboring vertical lines, you will see something like this. So on a line you will see, I don't know, maybe these three lozenges, and on the next line, interlaced with them, you will see, between these two we will see exactly one, between these two we will see exactly one, and so on. Okay, so there is a perfect bijection between positions of these interlaced, we start calling them particles, and the lozenge tiling. So as Vadim mentioned, once you know the position of the yellow guys, everything else is fixed, and they have to satisfy this interlacement. Okay. So from now on, essentially I will only draw the horizontal ones, like here. So this is a simplified picture. It doesn't exactly correspond to the picture before, but. And then, as I was saying, the most direct analog of the simple exclusion would be to have this particle jumping up or down with rates p and q. Like this one will jump up with rate p. This one will not jump up with rate p because it's blocked by these other two. Because they have to go to, it's like you cannot deposit a cube anywhere and still keep a lozenge tiling. But anyway, so you can imagine a dynamics where, you can even imagine it in infinite lattice. You have all these interlaced particles, they jump up, down with rates p and q, times there is an indicator that you don't overcome your neighbors, you don't violate the interlacements. So I will call this the single flip dynamics. Actually, the dynamics I will have results on is not this one. But before I go to the long jump version of the dynamics, let me recall a couple of things, which were, so it's kind of a reminder from the first talk to today. So what is the analog of the Bernoulli measures, which were the invariant measures for the simple exclusion? So they are given as follows. You fix three numbers, rho 1, rho 2, rho 3, which sum to 1, which will be the densities of the three types of lozenges. So you have just two independent numbers. And then, given these numbers, there is a unique translation invariance ergodic measure on the lozenge tilings of the whole plane, such that the three types of lozenges have these three densities, and such that they are Gibbs measures in the sense that whenever you condition on the tiling outside a finite domain, inside your uniform. Okay, so this is, in this sense, they are Gibbs. So given rho 1, rho 2, rho 3, there is a unique measure of this type. And as was, well, I don't remember whether it was mentioned, but if you look at correlations at some distance, like probability of having a horizontal lozenge here and one there, the correlation, the semicolon as usually is truncation. I'm looking at the correlation. this correlation decays like 1 over the distance squared. These measures have a determinantal structures. Higher order correlations are also given by determinants. So there is a lot of known about this. They are very good. The kernel in the determinantal structure is explicit, so very much is known. And as was briefly mentioned, if you look at the height function of an interface drawn for one of these measures, and you on large scales, the fluctuations away from the average. So when you fix ρ1, ρ2, ρ3, your typical interface has a certain slope determined by these numbers. If you subtract this average slope, the fluctuations will converge to a Gaussian free field, two-dimensional Gaussian free field with the usual log type covariance. All right, so I will mention this briefly. And in this sense, this is really the analog of the Bernoulli measures in the sense that, like for Bernoulli, that you can obtain by taking a circle and fixing the number of particles and then taking uniform measure. These measures can be obtained by taking a torus, taking uniform lozenge tilings of the torus with fixed proportion of the 3 types of lozenges and letting the torus go to infinity. So they are really the analog of Bernoulli measures, except that their correlations and height function fluctuations are really different from Bernoulli. Okay, so what is known about this spin flip dynamics? I'm focused on P different from Q. I'm looking at the growth model, not at the reversible process. So in a sense, not too much. The stationary states are not known. Presumably, well, you can imagine for every slope, there will be a stationary state with that slope, probably. But these presumably are very different from this Gibbs measure with slope ρ. There are numerical simulations where you start from interfaces which approximates a certain plane of a certain slope. You let the dynamics run, and you look at, for instance, you look at a point. You look how the height at that point. Well, it will increase on average, but you can look at the fluctuations away from the average. And the fluctuations seems to grow like a non-trivial power of time. And once more, so the state you reach for very large times is presumably very different from these Gibbs measures. So there is something you can obtain relatively cheaply.
There is a question.
Yes?
Why do you expect these special Gibbs measures to have something to see with the dynamics?
No, in fact, no.
Because, I mean, you have two things. You have the Gibbs structure and you have the transition kernel. To take the transition kernel uniform is kind of, okay, you need to understand why to take.
So your question was
my question is, for instance, does the stationary states have some, is it possible to think that they have some Gibbs structure with a kernel which is kind of different?
I think there is no reason to believe there will be still determinanta with another kernel. No, so the answer is, I think no. So the one-dimensional case where Bernoulli stays stationary is really a special case. The generic case is where once you add the drift, then the stationary state has nothing to do anymore with it. I think, okay. So, yeah. So as I was going to say, at least in the totally let's say in the totally asymmetric case where you just deposit cubes, there is an easy way to get the hydrodynamic limit. For this model, I'm not sure who did it first, but anyway. So if you take the height function and initially it converges to, it approximates some smooth profile. And then you take the height function at time t, but you rescale position and time by L and divide by L. So you're taking you're scaling space and time in the same way. So it's a hyperbolic rescaling. So one can show that this stuff converges almost surely to a limit, phi of x and t. And this limit is the solution of a certain first order PDE of this type, Hamilton-Jacobi type, dt phi plus certain function of grad phi equals 0. Where V is convex, maybe not strictly, but it's a convex function. And this is a solution is, well, you know, this kind of first order equations develop singularities in finite time. And so what kind of solution is that? It's a so-called Hopf-Flachs solution, so which can be expressed with a very compact variational principle in terms of this function V and of the initial profile. Okay, so this is something you can obtain by superadditivity type of arguments of the type developed by Timo and Reza Kanlu. But they don't give you what V is. They give you the existence. It's like for last passage percolation, or first passage percolation. You get the existence of this shape, some convexity, but I mean, so it's nice that you have this limit, but okay, it's hard to guess what V is. I think, okay, so I have no results on this model, nothing new. So I will look at the different one, which is a sort of long jump generalization of this model, and I will explain later that this actually corresponds to the model that appeared in Vadim's slide. Yes?
So this V should be related to the stationary.
Yeah, it should be like the expected probability, the expected number of triplets of lozenges in the stationary states. But yeah. But then yeah, sure.
But it does not depend on the initial, right?
No.
V is just universal.
Yeah, V is. I mean, no, I mean, the equation will not depend. Well, there will be an initial condition that depends on the initial condition, but the equation itself does not. So the long jump version of the process is informally introduced like that. You still have these interlaced particles. They still jump up and down with rate p and q, but the jump can have arbitrary length. There is always the indicator that you don't overcome your neighbors. Like, so just to be sure, I'm not saying that this particle jumps with rate q, and then once it jumps, it chooses a position uniformly. I'm saying that this particle, for instance, jumps with rate q here, with rate q here. So if you have 10 available positions below you, you will jump down with rate q times 10, and then the position where you land is uniform. So the more space you have, the quicker you move. Okay, so this is a sort of informal definition in the sense that it's easy to see that you can construct initial conditions where things go wrong. As I said, just because when you have a lot of space, you jump quickly, so you can construct. So here I have, you always give this example. It's kind of extreme example. Imagine these pictures goes on forever. So you just have in 3D, you have this empty corner. And if you look at the top particle here, it has an infinite space above. It's not blocked by anyone. So it will just disappear with rate. So I mean, it will disappear instantaneously. And then the two neighbors also are free now to move. They disappear instantaneously and so on. So I mean, of course, it's a very extreme situation. But you can construct situations where you don't have infinite spacing, but still particles go to infinity infinite time. So, well, okay. So let me make the link with the dynamics that appear in the Vadim slide. So this dynamics, at least in the totally asymmetric case, was introduced by Borodin and Patrick Ferrari in a paper that I think appeared, the 08 originally. So, well, if you know it superficially, maybe you didn't recognize it. But so this slide is just to make the connection. So the way they draw lozenge is a bit different. I mean, instead of, that's a choice. It's just in a different perspective. And also, what I call particles in this talk, there will be these horizontal faces of the interface. What they call particles are instead these ones, this type of lozenges here. Okay, that's a choice. So what you see here, here you see a transition where these two cubes have been removed here on the right. So in my language, it would mean that a certain particle has jumped down by 2. With their point of view, instead, what they say is that this red particle has jumped to the right by 1, but by doing that, he has also pushed this guy which was sitting on top. So it's just the same way. So, I mean, it's two different ways of seeing things. Either you say that in this transition, you have a particle jumping down by 2, or you say that this one has jumped to the right by 1 and has pushed this other guy. Okay, so I mean, in this case, you have jumps only of one, but then you can push arbitrarily many people above you. So it's the same thing. Well, it's the same thing in the total asymmetric case. All right, so let me mention a few things they proved. Not the whole result they have, but...
I'm sorry. So
yeah.
In their case also the red particle had more rate to jump than the one above?
No. The rate is always 1.
Right, it just takes...
Like, well, for instance, this one here it cannot jump because it's blocked by this other guy here. But this one has rate 1, this one has rate 1. So it's exactly in my case where P equal 1 or Q, well, maybe it's Q equal 1. All right.
But overall, the particle above
yeah.
has more rate.
Yeah, sure. Yeah. If you want, yes, sure. Yeah. Okay, that's also... Okay, so one result they have is the following. If they start from a configuration, this can be extended to other initial conditions, but at least let me concentrate on this one. Suppose you start from this kind of configuration where you have a kind of building, infinite building, and this is a floor around. So in terms of particles, it means the particles are put in this wedge-shaped, are just packed in this wedge-shaped region that extends to infinity. So all here they have these particles, and otherwise they don't. All right. So okay. So then they let evolve, and what they find is that if you take the height function at position xl time tau l divided by l, this converges to a certain something deterministic phi of x tau. And then you can see that this thing solves the certain first order PDE, as it was the case for the single flip dynamic, except that now this V is completely explicit. In the convention I'm using here is this function here. It's not a convex function of the gradient. You can see it. Well, I mean, but it's totally explicit. It looks a bit singular, but in reality, if you, well, I have not really said how I define the height function, but let me say the choice of height function I'm making is that if you are here, then the height, and you move in this direction E1, then the height function, I will say it increases by, maybe I say that it increases by 1 if I cross a lozenge and stays constant otherwise, like here, I'm not crossing a lozenge, and instead I'm staying at the same level. And here, for some reason, I'm saying that I'm jumping up by 1. So it's like I'm looking at minus the height with respect to horizontal plane. And same thing in this direction E2. I say that the height increases by 1 if you cross a lozenge and does not increase by 1 if you don't cross. So this is just to say that the slope of the interface is constrained in a certain polygon of space, and in this polygon all these signs are positive. So this stuff does not diverge except when you choose slopes which are extreme in the sense they correspond to interfaces where all lozenges are of the same type. Okay, I'm not sure I explained this very well, but anyway, so one of the results is that if you start from this initial condition, you have this hydrodynamic limit with an explicit function V. All right. Then they also prove that if you look at fluctuations away from the average height, there is a CLT on scale square root log L. So square root log of the time, because so here we are taking time of order L. If you divide by square root log L, and the fluctuation, you converge to a Gaussian random variable with a certain variance, completely explicit. And then if you look at large times, locally around the point, you will see essentially a Gibbs state, a Gibbs measure with the slope given by the hydrodynamic limit. I've not written down a statement here. Okay, so, right, so this was proven for this kind of initial condition. There is, as far as I understand, a more general class, but there is still a strong restriction. They have to satisfy certain certain Gibbs property initially. So it's quite restrictive as far as I understand.
So there's no critical direction where you would get other than Gaussian fluctuations?
So here it's looking at, well, it's not, so okay, if you start from this kind of region, then as time evolves, there will be a liquid region and a frozen region outside and the boundary. So what I'm saying is valid in the liquid region. So at the boundary, I'm not sure what you. Yeah, I mean, I'm not sure it's on your paper, but maybe it is. But yeah, anyway, in the liquid region is.
At the edge, you have the exclusion process.
On one edge, you have TASEP, I think, no? Mm-hmm. Okay, so my claim here was inside the liquid region. All right, so let me give a few new results. So the first result I have is that, okay, this is not a big surprise, but if I explain why it's true. So the first result is that there is a large class of initial conditions for which the dynamics is well defined, and initial conditions has to satisfy the following: that if you look along a column and you look at the spacing between, if you look at the position, let's say this is first particle, this is second, this is the third, and so on, and call this position Z1, the vertical position, Z1, Z2, Z3, and so on. If the spacing are such that Zn over n squared tends to 0 as n goes to infinity, then, so if, more or less, if the spacing between particles grows less than linear, then particles jump, no particle jumps to infinity at infinite time. Okay, so for instance, if you start from a configuration where all particle spacings are finite, are bounded, then it's fine. Is it clear? So also if, well, this is the second point is more important. So if you sample your initial condition from the Gibbs measure with some slope, then you stay in the Gibbs measure forever. So these measures are stationary.
And that's for arbitrary P and Q? Or that's
yes. So that's for yes. Yeah, here in this theorem, I'm not assuming. Yeah, I'm not in the totally asymmetric. So yeah, for these measures are stationary for arbitrary P and Q. Well, yes. And so once more, this is a kind of exception. So you should not think that this is the generic case. It's kind of a special feature of simple exclusion of this model, but it's not like a general feature. Well, then third point says that if you are in this stationary state, and if you look at the average increase of the height at some point, okay, not big surprise, it will increase linearly in time with some velocity. And the function V is the same thing as appeared in the Born-Ferrari hydrodynamic limit. By the way, in my theorem, there exists a positive, a non-zero velocity, and then it was Sunil Chita and Patrick Ferrari who managed to prove by some combinatorial identity that this V is the same as what appeared in the previous paper. Okay, so the height in a stationary state, the height function grows linearly in time in average. And if you look at fluctuations, they grow like the logarithm like a square root logarithm of time. So essentially, this line is telling you that it's very unlikely that the height increase at a certain point in time t minus the average height increase, it's very unlikely to be much larger than square root log t. This 1 over a squared, I mean, I could get better, but it's not important. It's something that goes to zero when a goes to infinity. So this also, again, is compatible with the result they have for their special initial condition, where they prove that height fluctuations on scale square root log t converges to Gaussian. Okay, so you have to think this stuff grows on average, but somehow if you look at the increase between time 0, time 1, and time 2, they are very anti-correlated, so that you don't have overall a variance growing like t, but only like log t. Okay. Okay, so actually also to be very precise, in my paper, I proved a weaker statement where I had some technical restriction on the slopes for which this was true. But then in a work in preparation with Sunil and Patrick, we removed, I mean, we have this full result without any restriction on the slope rho, which had no reason to exist, this restriction. Anyway, so this is one result. It's about stationary states and how in stationarity fluctuations behave. The second result is very recent. It appeared on the archive this week, I think. So we have a hydrodynamic limit. And in this case, we have to assume we are in the totally asymmetric case. So let's say we can only grow. So the result says, with my student Martin Legras, so the result says the following. Suppose your initial, so h without time is just initial condition. Suppose that initial condition is such that if you rescale it, it approximates a smooth profile phi naught. Phi naught is just, let's say it's assumed to be smooth enough, and its gradient is assumed to satisfy this inequality. These inequalities are just saying that nowhere you have frozen regions. This is just what it's saying, that nowhere, if you approximate this profile by just putting the stepped interface that sticks close to it, there are no macroscopic regions where you see only lozenges of one type. Because, for instance, if you had I don't know, a whole region where all lozenges are put like that, and for instance, you move in this direction, by my definition of height function, here the height increases always by 1, so you will have that the gradient in that direction is 1. So this is excluded by this strict inequality. So just to repeat, I require some smoothness and no frozen regions. And then the first part of the result says that there is a hydrodynamic limit. You converge to a certain deterministic phi, and this phi satisfies the Hamilton-Jacobi equation. Of course, it's the same v as just before. I mean, it has to be the same. And up to the time where singularities appear. So once more, this is a nonlinear first-order PDE. In finite time, for generic initial condition, what will happen is that the gradient will develop discontinuities. So then you don't have a classical solution anymore. So up to that time, you have this limit. And then, of course, natural question is what happens after that time. And there is, so at the level of PDE itself, there are various ways of defining weak solutions that go beyond the shock time, but there is a very more natural one, which is called the viscosity solution. And, well, I'm not probably you know, but I mean, viscosity solution can be either seen as I take this equation, put on the right-hand side epsilon times the Laplacian, so a little viscosity, then everything is smooth, and then I let this epsilon go to 0. There is a more intrinsic way of defining, but anyway. So this is a natural candidate. In fact, this is what we can prove, at least if the initial profile is convex. So if this phi 0 has a convexity in space, we can prove that even for time larger than t shocks, the same theorem holds, and then the solution is the viscosity solution. Just to say as a side remark, the main reason why we cannot prove this for all initial profile is mostly of analytic type, not so much of probabilistic type. Anyway, I can say something later if you want. Okay, so this is a second theorem. A few comments. So the function v is, well, if you stay away from the frozen region, from the extreme slopes, it's very well defined on C infinity functions. But due to this denominator, when you approach the region, well, if you think a bit, you make a drawing, you will see that this sign will go to 0. The denominator will go to 0 exactly in the situation where particles are very much far away. So. If you take initial conditions where the particles are more and more spaced, it corresponds to this sign going, to the argument of this sign going to 0. So when this is coherent. Now, when particles are very spaced away, they will move quickly. So this speed function will diverge. Okay. So the fact that this v has this divergence in this limit is one of the reasons why, one of the origin of the technical difficulties of the proof of the result. The second observation, well, this V is not convex, not concave. You can check So the theorem cannot be obtained by superadditivity type argument. So for the single flip dynamics, the typical thing you do is if you start, so let's say I'm doing TASEP in one dimension. If I start from this wedge condition, initial condition, it's very easy to prove by superadditivity that the height function started from this at time TL, space xl over L converges to some t times L of x over t, where L is a convex function, just by essentially superadditivity. And then when you start from another initial profile, something else, some initial profile h, then you can write h of x as an infimum over all y of h of y plus this wedge stuff centered at x computed at y. Okay, this is something you can always do. And then the single flip thing satisfies that if you start from an initial condition that is an infimum of various things, then you can couple all these initial conditions so that the property remains true at all times. So if your initial condition is the inf between two initial conditions, then at time t is still the infimum between the evolved two things. And then since all of them you can let them evolve, you know how they evolve, in the limit you get a solution of the type that phi of xt will be the infimum of phi 0 of y plus t times L of x minus y over t. Okay? And then you recognize that this is nothing but the Hopf flux solution of your PD. Now, this is if this kind of approach, which gives you automatically convexity of L, works if you have this so-called envelope property, that if you start from the infimum of two things, the evolved will be the infimum of the evolved. So in our model, unfortunately, well, maybe it's not by chance, but this property is not true. We cannot obtain the result by superadditivity. Otherwise, automatically, we would have our speed function to be convex, which is not the case. Okay, so we have to do things differently. So the important point in this approach is that at the microscopic level, you have a sort of variational principle that then survives to the macroscopic level. The reason why, so in the case of convex initial, our function V is not convex, but still if the initial profile is convex, there exists a variational formula called Hopf formula for the solution of the PDE, and we use this fact. But in contrast with the convex V case, we don't have at microscopic level, we don't have a variational, we don't have this envelope property. So, okay, so maybe here I got a bit messed up. Anyway, so another observation is that for the initial condition considered by Alex and Patrick, if you look at the characteristic lines of the PD, they never cross, so they don't have creation of shocks. Instead, if you take an initial, generic initial profile, even convex, in general, you will form shocks. Maybe a last comment about the result is that in contrast with what they did, we're not using integral probability methods to express exactly coherence by determinants or stuff like that. Okay, so it's more probabilistic type of proof. Yes, okay, I guess I have 5 minutes or something like that, is correct?
Yes,
7, good. So in 7 minutes, I will make at least a heuristic link with the 2D KPZ equation. So, okay, now you have, for instance, look at your evolution in starting from a stationary state of slope rho. So what one expects in heuristically is that if you look at fluctuations on large space-time scales around the well, I'm subtracting off the average increase of the height. One expects that the fluctuations are in some sense described by a stochastic PD of the following type. You will have this usual smoothing term, the space-time white noise. And then there will be the first nonlinear term you write down. So in one dimension, you would have something like constant times gradient squared. Now here you are in 2 dimensions. So in general, you will have a quadratic form of the gradient. And now, so it will be gradient times a certain 2 by 2 matrix Q times the gradient. And this 2 by 2 matrix should be nothing but the Hessian of the function V computed at the row at which you are, that you have chosen as your stationary state. Okay. So, well, okay, I don't know how to give a meaning to this equation, but I mean, this is not the point of my talk. And okay. You could think that the noise is smoothed out at small scales. I mean, here I'm interested at large scales anyway. So anyway, it's just to motivate what will come. Okay, so this is what is believed. And now, in contrast with one dimensions where the nonlinearity is just C grad square, and the sign of C doesn't matter. You can always change height to minus height, and then you change the sign of the C. Here in 2 dimensions or higher dimension, you have the situation is richer. So there are two situations. So when the matrix Q has a signature of constant type, so it has 2 eigenvalues of the same sign, plus plus or minus minus, then one refers to this equation as the isotropic KPZ equation. While when the signature is mixed, one refers to it as an anisotropic KPZ equation. And this, of course, depends on the convexity properties of V, because remember, Q is just the Hessian of V. So, for instance, in the single flip dynamics, we don't know V, but we know it's concave. So it will be convex. So it will be in the first case. It will be plus plus signature. In our case, you compute the signature. So Alexei and Patrick did. It's not a big computation. It turns out to be plus minus everywhere. For every row, you have a positive and a negative eigenvalues. So it will be in the anisotropic class. So, the fact that you fall into one of the two classes is believed to have a big effect. So it is predicted by Wolf that in the anisotropic class, the nonlinearity will be irrelevant in the sense that on large time scales, it is as if it were not there. And if it is not there, you just have the stochastic heat equation with additive noise. Fluctuations will grow like square root of log t. And this is in agreement with the theorem I had on the growth of fluctuations. Well, I have an upper bound. But in the isotropic case, so plus plus, for instance, so which means like the single flip dynamics, the nonlinearity should be relevant, so should change the growth exponent. There should be a growth of fluctuations like some non-trivial power of time, and in fact, this is observed numerically. There is no proof of this. So the things fit. And okay, if maybe I will spend the last 3 minutes just to explain that by modifying a little bit the model, taking a limit where things become easier, we managed with Alexei and Ivan to go beyond this square root log t bound on fluctuation and to really prove that in some limit, the fluctuation do follow a stochastic heat equation with additive noise. So this I will do a bit briefly because of time. So remember in the borrowed in Patrick pictures, particles jump by 1 and can push people. So, but they jump by 1 with rate 1 if they can. So suppose I modify a little bit the dynamics. I have this red particle wants to jump. It will jump so not with rate 1, but with a rate that depends on the distances between it and these 6 neighbors. I don't define what B, D, R, C are, but essentially I think that A is the distance between this guy and this guy, B is the distance between this guy, and so on in clockwise order. Anyway, there is a choice of rates, which depends on a parameter R, in 0, 1, and you let particles jump with rate given by this, and if they have to push people, they do, and so on. Okay, it's a specific choice of rates. You can check that if you let this parameter go to 0, you are back to the usual borrowed in Ferrari dynamics. So something we noticed with Ivan is that for this particle dynamics, it's still a driven dynamics, but you can write down explicitly the invariant, well, in a sense explicitly the invariant measures, which turned out to be of Gibbs type. Okay, so then what we do is to take a limit where this parameter, okay, remember, to recover the Brownian Ferrari dynamics, you have to take R to 0. If you do the opposite limit, R going to 1 instead, it turns out that things simplify. So you have to take R to 1, like e to the minus epsilon, at the same time scale particle distance by 1 over epsilon, and then see what happens, and scale time. So the result says the following. You should imagine that the initial condition in this theorem, in the initial condition you have, well, these particles which are spaced by distances 1 over epsilon plus a little bit like 1 over square root of epsilon. So on scale 1 over epsilon, they are just equally spaced, and then you have little fluctuations initially. Then what happens? So the first statement tells you that if you weight times of order 1 over epsilon, on these time scales, particles just move on straight lines. So it's a hydrodynamic type limit. So on that time and space scales, things just move with speed v. V is something explicit I will not write down. Then if you look at fluctuations of order 1 over square root of epsilon, then the position of the particles around from their typical position converges to the solution of a set of linear SDs. So in this limit, the fluctuations away from the hydrodynamic limit become driven by a set of linear SDs. And then once you have this linear system, you can compute all the correlations you like. So these are the correlations. You can see them as correlations between height fluctuations at time x, at time t position x, and the same thing at time s and position y. Once you have done this limit, you can compute everything. And what turns out is that if you look at in the right way, you recover exactly the correlation of the stochastic heat equation. What I mean, and this will be my last slide, what I mean is the following, that, well, initially you have your height function. This is time, I don't know, 0. Then you look at time t, and the later, no, maybe s, and the later time t. If you choose a certain particular direction in space-time, which is has a meaning of a characteristic direction, and if you look at correlation along this line, this is what my choice of times and spaces is doing, then the height correlations along this characteristic line will converge to those of the stochastic heat equation with additive noise. So it's like in this limit, the nonlinearity has disappeared. Okay, it is what it is. So if you choose another direction instead, you have a much faster decay of correlation. So this should recall what Patrick mentioned yesterday about slow correlations in the TASEP. If you choose the right characteristic direction, you will find correlation decay very slow in time. If you choose other direction, you will not. So a similar phenomenon of slow correlations along a characteristic direction should hold for the true discrete Brownian-Ferrari dynamics, but that is at the moment out of reach. So just to conclude, okay, so we started with a single flip version of the dynamics, which looks very natural. Unfortunately, apart from the hydrodynamic limit and maybe very soft argument, very soft results, other than that, it's very hard to say anything at the moment. So we look at the longer jump version, which looks natural at least. That can be analyzed in detail. There is some integrable structure behind that guarantees that invariant states remain Gibbs. But other than that, I'm not using this structure for the dynamics itself. And then once more, a remark is that somehow we have changed the dynamics and we have also changed the universality class. So the first single flip dynamics and the long jump one should fall in these two different classes. So it's not like an innocent change we made. Yeah, that's it. Thanks.
Okay, Fabio, thank you very much. We're a bit late, so maybe there's time for a short... We have time? No, I'm worried about my lunch.
So can you say a bit about how you compute the V in the
without using integrable probability?
No, well, V in principle, it's well, once you know the stationary states, it's easy to write V as the average of something at equilibrium, in the equilibrium state. But the function is quite complicated. It's easy to see it's positive and stuff like that. Then if you really want to spit out the precise function with these signs and so on, you have to use some identities of the inverse Castellan matrix, and that was done by Patrick and Sunil. What I was saying is that, well, sure, we use a lot the properties of the determinantal property of the stationary states for these kind of things. What I'm saying, what I meant by saying I'm not using this integral probability structure is that, in contrast with what Patrick and Alexei do, we don't have exact formulas. I don't have exact formulas for the current, like the moments of currents or something like that. But as far as stationary measure is concerned, yes, I need it to be what it is.
So is there a way to see directly the stochastic heat equation from the anisotropic KPZ? Like if you just look at this anisotropic KPZ, which is kind of conjectural thing.
Yes.
So either, so can you just looking at that see stochastic equation in it? So where is it hiding here?
Well, I mean, no. Well, if this is no, I didn't get the question. So the point is that. So what Wolf did, as far as I understand, to do some renormalization step and to prove that by, I don't know, doubling the scale or something like that, if here in front you have some coefficient, I don't know, C, then by doing so, this C will start decreasing. So on large time scales, this nonlinear term will disappear, and then what you're left with is just the stochastic heat equation. Yeah, I think he did some kind of this, something of this type, like at first order in one loop approximation. And then he checked that if instead the signature is plus plus, then instead this stuff starts to grow. So and then it's like it becomes more relevant, and then it's hard to say anything more. I think this is a very short summary of what he did.
No other questions? Let's thank Fabio and all the speakers this morning.